For our first actual Algebra 1 unit, we're looking at Introduction to Functions. So our goal is to differentiate between relations and functions and evaluate functions for inputs and outputs. So there's really two things you need to be able to do to earn that 3.0 level. So these are the skills that will help you achieve that. And we'll be going a little at a time here. So here's your work plan for the unit. We're going to be working on 1.1 for 2 days and then working through 1.2 the rest of the week. And when I return to class for the flex day, we'll be able to go over anything from those sections that you'd like to cover before you take a checkpoint, which is basically your first assessment for the unit. On page 2, you're going to see the types of problems we want you to be able to finish or complete by the time we are done with this unit. So it wouldn't be a bad idea to take time to read over these before moving on to the actual notes. So you can pause the video, whatever you want to do. But these are the types of problems that you would need to be able to complete or similar types of problems in order to show that you're at a 3.0 level. Also, maybe being able to create these types of problems on your own. So if we look at 1.1 notes, we're talking about what are relations in math. And with that, we're going to be able to represent relations as graphs, tables, ordered pairs, and mapping diagrams. So relations pair inputs and outputs and can be displayed in various ways. We do have an error here in the notes I'm going to ask you to fix right away. The input is known as the independent variable. So we had these backwards. And the output is known as the dependent variable. So make sure you do have that, that's important. And when we say variable, if you remember from pre-algebra, variables are letters in math. So typically our input is the variable x and our output is the variable y. As an ordered pair, a relation has an input x paired to an output y. As a table, we have the inputs of x and the outputs of y. You could also see tables vertically, x's and y's. We can also show mapping diagrams. They're like bubbles. So here's our input x bubble and our output y bubble. With a mapping diagram, we want to make sure we follow some special rules. And this is the only visual of relations that we get picky about this. So in the x bubble, you're going to make sure it goes from the least to greatest, so 1 through 5. Same thing in the y bubble. The least number is -6, the greatest number is 7. And then depending on the relation, in this case it's given to us, the 1 pairs to the 3, or it maps to the 3. 2 maps to -6 to create a pair. So far we have the pair 1, 3 that we can now write as an ordered pair. We have 2, -6. 3 is paired up to 7. 4 was paired with -4. And 5 was paired with 7. So now we've represented this relation as a mapping diagram and as a set of ordered pairs. We can also represent it in the table. All of the inputs, or the x coordinates, if we were to refer back to ordered pairs. So x was 1, 2, 3, 4, and 5. Those don't have to be in order, but you do have to make sure they're still paired with the same outputs. So we said 1 was paired with 3, 2 to -6, 3, 7, 4 had an output of -4, and 5 had an output of 7. So now we have a mapping diagram, ordered pairs, and a table to represent the exact same relation in different ways. And the last way we can do that is with a graph. So whether you want to pay attention to the ordered pairs or the table or the mapping diagram, you need to graph those points. So remember from pre-algebra, we always graph our x, y in order. So first with 1, 3, we want to move 1 on the x-axis and 3 on the y-axis. 2, negative 6 is 2 on the x, negative 6 on the y. 3, 7, 4, negative 4, and 5, 7. Notice in the directions it says, oops, sorry, I'm underlining the wrong spot. Do not connect points unless told to do so. Not all graphs have to create shapes. So we're going to go ahead and leave this unconnected or disconnected for this problem. So let's try another set of a relation. We're given the graph, so you could choose if you want to now create a table, ordered pairs, or a mapping diagram. Just like the pre-algebra unit, we practice reading ordered pairs, so we'll go ahead and translate the graph into ordered pairs, starting with this bottom left. So it looks like the ordered pair is x at negative 4 and y at negative 4. Then we have negative 2, 4, and it doesn't matter which ones we do first, second, or anything. We just want to make sure we pair the numbers up correctly. 1, negative 2 is one of the other pairs, and 3, 1. As a table, and again, you could do that side to side or vertically. I'm going to go ahead and do a horizontal table side to side. We can either keep reading off the graph, or we can now use the ordered pairs. I'm going to go ahead and refer to the ordered pairs. Remember, the first number is the x, so those are all of our inputs. And the second value in each ordered pair are the y's. As long as you keep the ordered pair paired up in the table, the order won't matter. Negative 2, 4 could have been the first entry in the table. That's up to you. Just make sure whatever it came as from the graph or the ordered pairs, the same numbers are still paired up in the table. And then for our mapping diagram, we have our input bubble and our output bubble. Whether you make it circular, rectangular, I don't care. But this is the one case where we want to make sure we go least to greatest for both the x's and the y's. So the smallest x was negative 4, followed by negative 2, 1, and 3. The lowest y value was negative 4, and then the next was negative 2, 1, and 4. Now we have to make sure we map or draw the arrows correctly. So negative 4 should map to negative 4. Negative 2 should map to positive 4. 1 should map to negative 2, and 3 should map to 1. So that is our second relation in the notes, represented in our 4 different ways. There is another way to represent relations, which is equations. We're just not quite there yet. Here we have a relation of a table to represent the homecoming dance tickets. So it says describe the inputs and outputs of the relation in context. So it looks like every input represents the number of tickets probably purchased. And then let's talk about the outputs. Every output represents the price paid for tickets. So depending on how many tickets you buy, you will know your price. I promise you my handwriting is actually a lot better than this. It's just difficult with the computers and the stylus. Sorry about that. But the inputs are the tickets and the outputs are the prices. How did I decide that? Well, it has that table format. We usually put our x's and then our y's. We always put our x's on the left, y's on the right, or x's on top, y's on bottom if you have a horizontal table. So if you're asked to use context in a problem, that means what is like the real world scenario? How do you put it into context? Now we're being asked to take this relation as a table and represent it as ordered pairs. So remember, that just means write the x and y, keeping each x paired with the y across from it as you saw it in the table. And then, using those ordered pairs or the table, we want to represent the relation as a graph. Now, we weren't given very much on the graph as far as like labeling. So let's think about, we had the x-axis is horizontal, and that was tickets. So you could put number of tickets, tickets purchased, but we'll just put tickets like the table said. And it looks like we need to fit 0, 1, 2, 3, and 4 in this graph. So we can space that out if we want. There's plenty of room. So I'm going to go every other unit. And even though we don't need 6, I'm just going to go ahead and label out to the last value. And then Y was supposed to be the price. So after you buy so many tickets, you'll know your price. And it looks like we need to fit $0, $12, $24, $36, all the way up to $48. So let's go by 4s, just so we hopefully can fit them all. So we'll have 0, 4, 8, 12, and we've got it. If I go by 4s, I can make it up to the highest value of 48 that we were given in the table. Let's go ahead and graph the ordered pairs. And we weren't asked to connect the points, so we're going to leave them separated like this. Not trying to create a line. Although we could call this a linear function. We're just not in that unit yet. So for now, just graphing the ordered pairs as they were written. And the second part of the problem says to explain why the inputs and outputs are restricted to the first quadrant. So if you remember from pre-algebra, we have 4 quadrants on a graph. We have 1, 2, 3, and 4. So why are we stuck in the first quadrant in terms of the context for this problem? Well, tickets are all of the positive x values if we're in the first quadrant, and price is all of the positive monetary values in the first quadrant. If we tried to go to quadrant 2, we would have negative tickets because we would have -1 on the x-axis all the way out to -10 if we wanted. But you can't have a negative amount of tickets, so this quadrant doesn't make sense. We don't want to be in quadrant 3 because that would be negative tickets and negative prices on the y-axis. Neither of those could exist. Quadrant 4 doesn't work because even though we have a positive number of tickets, which is normal, we wouldn't be paying negative prices. So the only quadrant that makes sense is quadrant 1. So inputs and outputs must be positive numbers, which is where they would fall in quadrant 1. Everything there is positive, so quadrant 1 just in parentheses there. The number of tickets and price values cannot be negative in a real world situation. Now, maybe you could lose money, but that's a whole different case than what we're talking about here. So we'll just